In this video, I'm going to solve two exercises from entrance exam of graduate school of Tokyo Institute of Technology. These are very good exercises to understand the epsilon-delta definition of the continuity. This is the first problem. In this problem, f is a continuous function on the interval from 0 to infinity such that the limit as x goes to infinity of fx exists with finite number a. Under these assumptions, we are going to show that f is a uniformly continuous function on the interval 0 infinity. In the second problem, f is a uniformly continuous function on the interval from 0 infinity such that the capital F defined by the integral from 0x of fx is bounded. This is the assumption, the bounded on the interval from 0 infinity. In these assumptions, we are going to show that f is also bounded on the interval from 0 infinity. Let me start to solve the first exercise. This is an image of the function f of x. This is x-axis and y-axis, and this is a graph of the function fx. For this function, there exists a limit of fx as x goes to infinity. The graph of f can be written like this way. First, we fix epsilon arbitrarily from the assumption the existence of the limit of f of x at infinity. Expressing the limit by epsilon-delta definition, there exists a positive large number m such that for all x in the interval 0 infinity, if x is greater than or equal to m, then the modulus of f of x minus a is less than epsilon. This is a epsilon-delta type definition of the limit. This means in the image, if x is greater than or equal to the large number m, f of x is sufficiently close to the limit a. Okay? As you already know that the continuous function is uniformly continuous, that is from the uniformly continuity of the function f on the closed interval from 0 to m is a number as above. There exists a positive number delta such that for any x and y in the interval 0 and m, if the difference between x and y is less than delta, then the modulus of f of x minus f of y is less than epsilon, which is the epsilon-delta definition of uniform continuity. When x and y are greater than or equal to m, the modulus of fx minus fy is written by fx minus a plus a minus fy by the triangle inequality. This guy is estimated like this way. Thus, from the first computation here, these terms can be estimated by 2 epsilon. When x is less than or equal to m, that is x in the interval 0 m, and y is greater than or equal to m, and the modulus of x minus y is less than delta. That is, in this image, this is x and this point y, and the difference between them is delta. You can easily find that the modulus of x minus m is less than or equal to the modulus of x minus y, which is less than delta. Then the modulus of f of x minus f of y is less than or equal to f of x minus f of m plus f of m minus f of y from the above inequalities of the epsilon. The right-hand side can be estimated by 3 epsilon. Okay? From the symmetry of the variable x and y, this argument is also true when y is less than or equal to m, x is greater than or equal to m, and the modulus of x minus y is less than delta. Thus, we complete the epsilon delta argument for any x and y greater than or equal to 0. That is, for any x and y in the interval 0 infinity, if the modulus of x minus y is less than delta, then the modulus of fx minus fy is less than 3 epsilon. Therefore, we complete the proof of the first exercise. Next, let me solve the second problem. Now I'm showing the second problem. We want to show the boundedness of f in the interval 0 infinity. The proof is based on the contradiction argument, such that the function is unbounded on the interval 0 infinity. The continuity of f implied that f is bounded on any interval from 0 to m, where m is any large positive number. Thus, f is unbounded at the spatial infinity. That is, there exists a sequence xj in the interval from 0 to infinity such that xj goes to infinity as j tends to infinity, and the limit of fxj with the modulus goes to infinity when j tends to infinity. Considering the positive part or negative part of f of xj, we can choose the subsequence xjk of xj such that the limit as k goes to infinity f of xkj goes to infinity, or the limit of f of xkj goes to minus infinity. Without the loss of generality, here we can assume that the subsequence satisfies that the limit of xjk is plus infinity as k goes to infinity. Here we use the uniform continuity of the function f by employing the epsilon delta definition of the uniformly continuity with epsilon 1. That is, we chose 1 as epsilon in the epsilon delta definition, which implies that there exists a positive number delta such that for any x in the interval 0 infinity, if the modulus of xjk minus x is less than delta, then the modulus of f of xjk minus f of x is less than 1. Here we remark that the delta can be chosen independently, uniformly on the xjk and x. In the last inequality, we can easily see that f of x is greater than f of xjk minus 1. Now we consider the capital F of xjk, which is defined by the integral from 0 to xjk of f of x dx. Dividing the integration, we can easily say that f of xjk is equal to the integral from 0 to xjk minus delta half plus integral from xjk minus delta half to xjk of f of x dx. From the boundedness of capital F, the first integral is bounded by some positive constant c. In the treatment of the second integral, we use estimate of f as above. In this integral region, the difference between xjk and x is less than delta. The function f is bounded from below by xjk minus 1. Thus, this integral is bounded from below by f of xjk minus 1 times xjk minus xjk plus delta half, which is equal to f of xjk minus 1 times delta half. This line goes to infinity as k tends to infinity. Thus, the capital F of xjk goes to infinity as k tends to infinity, which contradicts to the boundedness of capital F. Therefore, we complete the proof of the second exercise. Thank you very much for watching. See you in the next video.